Hello, in this lesson, I'm trying to summarize some of those important points that we mentioned throughout the semester by going over this entry quiz to calculus, okay? I don't know if you guys have noticed, this quiz covered a lot of materials that we actually covered in this class throughout the semester. It just, we didn't mention this quiz yet. Okay, so here's this this quiz. Let me make sure you can see it. Yeah, this is the one. So I'm going to take this lesson to explain to you, right, some of these questions that we need to understand. Okay, so why they're right, why they're wrong, and so in that way, you guys can get in calculus, at least in these cases, you're good to go. Okay, some of the questions may show up on your final exam because we covered many of them during the semester. Okay, so now let's go over these questions one by one. Okay, all right. Here. Are you ready for calculus? Okay, so this quiz is a collection of questions available in the calculus textbook at the beginning of the course. So the author of the calculus text, James Stewart, he put together these questions in the older version of the calculus text to see if a student can get them all, can get 100% of them right. Okay, so for example, the first one, right? It says, if x is any real number, then the square root of x squared is equal to x. We covered this a long time ago, didn't we? Of course, this is wrong. This is a false, right? Of course, this is a false. We can easily give a counterexample, right? For x equals to -1, and that is a counterexample. This is a false, right? So this will be a counterexample for that. Number two, question number two, let me use a different one, use one, okay? Question number two says the square root of p plus q, I'm sorry, the square p plus q is p squared plus q squared. And of course we know this is wrong, right? P plus q squared, and this is a very common mistake, by the way. This is a very common mistake we see in calculus, okay? So p squared plus q squared is not, p plus q squared is equal to p squared plus q squared plus 2 times pq. Okay, so this is wrong. And this is right. Okay, so how do we show? It's just a FOIL this, right? FOIL this piece. Number three is the square root of a times b is equals to root a times root b. This is correct. Okay, this is correct. As long as a, b, they're in the domain. Okay. And the other common mistake is a squared plus b squared, right? And does this equals to a plus b? Of course, this is a false. Okay, this is a false. Do we have a counterexample for it? Okay, so this is a false. False. False, right? I have the counterexample, say a equals to 2, right? b equals to -2, right? You have so many, there's so many examples, but we really just need one, right? So we look at the left-hand side. So we're giving a counterexample. And this counterexample is a equals 2, b equals to -2. So we have a is, sorry, a is 2 squared, b is -2 squared, right? So the left-hand side will equals to square root of 2 squared plus -2 squared, that's going to be 8. And that's equals to 2 times √2, right? 2 times √2, but a plus b is 0 in this case. A plus b is 2 plus -2, that's going to be 0. 2 plus -2, that's equals to 0, right? So that's not true, false. Number 5 is this true or false, right? So 1 plus t times c divided by c. And the answer we get here, okay, this is a common mistake. Okay, 1 plus t. So what the student did, okay, the typical mistake, the student just cross out the c's. You can't, okay, so this is a false. False. Okay, what should be done is that the left-hand side, this will be right? You take the c, divide it into 1, so you get 1 over c plus t times c divided by c. So in the second term, the c and c can reduce, so you get t. Okay, so this is right. Top is wrong. Okay. Number 6 certainly is a very bewildering mistake. Okay, 1 over x minus, it's kind of creative mistake, okay? It's a kind of creative mistake. This is a false. Okay. This mistake is actually rather serious. This demonstrates the student has great lack of experience with fractions. Okay, but here I'm going to give a counterexample. I'm going to give you a counterexample. Okay, for example, I have x equals to 3, y equals to 2, right? And the left-hand side will be equals to this 3 minus 2. 3 minus 2, and that's going to be 1 over 1 equals to 1. The right-hand side, right? The right-hand side, oops. Oh, let me try to use them in the same similar format. So this is right. The right-hand side, which is 1 over x minus 1 over y, right? X is 3, y is 2. In this case, we need to find common denominator. And that common denominator is 6, okay? So 1/3 equals to 2 over 6. And 1/2 equals to 3 over 6. So this equals to -1 over 6 on the right-hand side. And 1 certainly is not equals to -1 over 6. So that makes a counterexample, okay? Number 7. Okay, at any time during this lesson, and you want to try your own, okay, feel free to do that. equals to 1 over a minus b. This is correct. This is correct. Okay, this is correct, right? Because on the right hand, on the left hand side, right? On the left hand side, we have this expression, and in the denominator, we have the same denominator, x, right? So we just have to do a minus b. We keep the same new denominator, and then we're going to multiply the top with x, multiply the bottom with x. Anything times 1 stay the same because x over x is 1. So the top is going to be equals to 1. The bottom is going to be a minus b. So that's how the left is the same as right. Okay, so this is a correct, and the left equals to right. Left equals to right. Okay, so all of these questions so far has been kind of algebraic. Okay, number eight. Number 8 is a very general statement. Number 8 is a general statement. It says f is a function. If f is a function, then f of s plus t equals to f of s plus f of t. In this semester, we've done a lot of function notation, right? So if you want to pause to think about this question, is it true or false, right? If true, you have to prove it is true for every function we have encountered. If it's false, we just need a one counter example. Feel free to pause and then come back and come back. Well, the answer is it is false. Why it is false? I just need to give you one counter example. Okay, it says if f is a function, imply that f can be any function. Okay, so I'm going to take this function, which equals to x squared, right? So what is f of s plus t? F of s plus t is s plus t squared, right? What is f of s? F of s is s squared, right? F of t is t squared. Could we say that if this is true, right? Could we say, is that true? That is s plus t squared. Is that equals to s squared plus t squared? We just talk about that p plus q squared, right? We just look at that, we just talk about this is a false, right? If this is a false, certainly that this is a false, right? So of course not, right? Of course not. And this is not the only function, right? So of course not. So, and we'll have numerous such examples. Of course, we only need one example. For example, if you put a function equals to say 2 to the power e to the power x, 2 to the power x, right? And try that. Does f of s plus t right? That's going to be 2 to the power of s plus t, right? F of s. I'm just trying to say there are lots of such examples, so we cannot take it that way. So this is s, right? And this is t. right? Oops. Can we say that 2 to the power s plus t equals to 2 to the power s plus 2 to the power t? Of course not, right? That's wrong. That's wrong, right? Because 2 to the power s plus t, what is right? 2 to the power s plus t is 2 to the power s multiply 2 to the power t. You see, right? And you can also take some trig functions, for example. So this mistake, right? If you put s sine x, right? You also draw the same conclusion. Okay, so f of s, f of t, you're just plugging in. So that is completely wrong. Okay, so very common. I can hardly say it's a common mistake, but it is a very serious mistake. Okay, so you can see that is not true, right? S plus t. In the case of sine s plus t, right? Apparently they're not equal because sine s plus t equals what? Sine s cosine t plus cosine s sine t, right? So they're certainly not equals to sine t plus cosine t. But anyway, we have lots of counter examples to counter this statement. Okay, it's a terrible mistake. It's very, very bad. Okay. For the same reason, let's look at number 10. Let's look at number 10. Okay. Because when you are in calculus, you're dealing with functions all the time. Okay. So can we say f of 3x equals to 3 times f of x? Right? If f is a function. Can we say that? Of course not. Of course not. Right? And the examples, there are numerous such examples. For example, just use x squared, the simplest example. Right? F of x squared. Right? What is f of 3? What is f of 3x? F of 3x equals to 3x squared. Whoops, squared. And what does that equal to? Equals to 9x squared. What is 3 times fx? It just equals to 3 times x squared. You see, they're very different. They're very different. And you can have numerous such examples. Number 11. Okay, if f is a decreasing function and x sub 1 is less than x sub 2. Okay, so if f is a decreasing function and input x sub 1 is less than input x sub 2, then f of x sub 1 is larger than f of x sub 2. Okay, this is the definition of decreasing function. Okay, so this is right. Okay, this is the definition of number 12. right? So if f is a decreasing function, okay, so I'm just kind of taking a shortcut. Okay, if x is an increasing function, and that is less than, and that is right as well. Okay, in fact, you're going to see these two statements, two definitions in Calculus 1 textbook once again at the beginning. Okay. Number 13. Number 13. Okay. If f and g are functions, f, g are functions, then f composite g, g composite f, they are the same. Is that right? Of course not. Of course not. No. Okay. I hope you remember that we have a composition case in f of x is x squared. Okay. G of x is cosine x. Okay, we once have done this example, haven't we? Okay, so recall we've done this, and I think at the time I also mentioned this. Okay, so what is f composite g? F composite g is saying f of g of x. Right, that's f of g of x, that's f of cosine x, and that's going to be equals to, and then we apply the f, so cosine x is going to be squared. And that is going to be cosine square x. Okay, that's the same. However, g composite f, x equals to g of f of x, right? And that's going to be g of f is x squared, right? So this equals what? This g of x squared is just going to be equals to cosine x squared. So if you look at the difference, right? The former, right, is a cosine x multiply cosine x. The latter is cosine x times x. So of course they're different. Of course they're different. Okay. So be very careful. Number 14. If f is a one-to-one function, if f is a one-to-one function, then f inverse equals to 1 over f. This mistake, okay, comes in many different shapes and forms. Okay, this mistake comes in very many different shapes and form. Of course, I already told you it's a false. This is a false. Okay, common mistakes are, for example, people will say, hey, arc sine equals to 1 over sine x. This is a very common mistake. Okay, and these two functions are not the same at all. We know arc sine, right? Take the input, which are ratio, right? Arc sine takes ratio as input, produces angle, And the angle is going to be in the interval between -1 to +1. I'm sorry, between -pi/2 to pi/2. Like that. Okay, between -pi/2 to pi/2. Okay, so the input is a ratio. How about sine? Well, if you look at the order of operation for sine, right? So this is for arc sine, right? That is a flow. 1 over sine x. 1 over sine x. All right, if you look at the 1 over sine x, the trajectory is, the flow is very different. X, first of all, and as the denominator for x, because it's in the denominator, we have to guarantee it is not going to have a ratio equals to 0, right? So we're going to do sine x, but because of this situation we have, we should require x cannot equals to k pi. Okay, because k pi will cause sine x equals 0. And so first of all, you can see there's a different domain requirement, right? The requirement for domain are not even the same. Okay, so this x is from -1 to +1. And this x can be any real number but multiples of pi. And once we get one, we'll get sine x, and then we take the reciprocal. We take the reciprocal of sine, and then that's the flow. So you can see these two are entirely different function. Besides, 1 over sine x is a cosecant x, right? It's cosecant x. So these two cannot be the same. But we see this mistake very often in calculus classes, which shows that some of our students really is not fully prepared for, for the next class. Okay, so there are numerous other examples you can think of, okay? So try and, well, don't make this mistake. Don't make this mistake. Now, let's look at number 15. It says, you can always divide by e to the power x. And the answer is true. Because okay, because what? Because e to the power x is always a positive. Remember, we emphasize, and we use this many times, right? E to the power x is positive for any real number. For any real number x. So that's the range description for e to the power x, which guarantees that you can always divide by e to the power x because it's always a positive. Okay. Number 16. Number 16, this gets interesting. Okay. So if 0 is less than a, less than b, right? And here we go. Then we say, then ln a, natural log a is less than natural log b. Is that true or not? Well, when we assume a is greater than 0, b is greater than 0, that these two quantities are in the domain. The question is, will this be true, right? It is true because ln x is an increasing function. Ln x is an increasing function. We graph this function, right? It keeps, so increasing function means that as the input is getting larger and larger, the output is getting larger and larger. Okay, so that is true. So let me make just a little bit adjustment to just remind you. Okay, this function is an increasing function. This function is an increasing function. It keeps going up. So for A is less than B, for any number in the domain of ln x, it's going to be always keep going up if the input keeps increasing. All right, so we're doing pretty well so far. Let's look at number 17. 17, okay. If x is positive, then ln x to the power 6 is equals to 6 times ln x. So the domain is guaranteed. No question about the domain. But will this be true? Well, in the lessons we talk about, and there's one example, which is solving equations, right? In that solving equation case, we once dealt with ln x squared and that sort of thing. So I'm just going to go straight. They're not the same. Okay, so this is equals to the base multiply itself 1, 2, 3, 4, 5, 6 times. Okay, 6 times ln x is equals to ln x adding ln x 6 times. So they are different. 3, 4, 5, 6. Okay, no, they're not the same. Okay, the point of confusion here is that the latter, okay, this expression actually equals to ln x raised to the power 6. These two are equal. You can see the power is, the first one power is for ln x, but this power is for x to the power 6. So they're very different. So ln, so in this case, it's x times x times x times x times x times x 6 times, right? So make sure you understand that. Number 18. Number 18. Number 18. Okay. If x is a positive, okay, and a is a positive, a is greater than 1, then ln x over ln a, okay, is equals to ln x over a. How? So we have guaranteed that because ln 1 equals to 0, so we guarantee there's no worries about left hand side have a 0 denominator. Would that be the same? Will that be the same? The answer is no. Okay, I'm screaming. Imagine I'm screaming at this. Okay, no. Okay. Well, for the left-hand side, this is a serious confusion between, we've talked about similar mistakes, right? This left-hand side is related to change of base formula, okay? And this equals to log base A of x. And this one equals to ln x minus ln a. You see, they're very different. They're very different, but yet this is a very, very common mistake. Very, very common mistake, okay? You can plug in numbers. You can plug in numbers, Okay, for example, I can give you an example to make you to help you to understand, right? Suppose I'm going to choose x equals to I'm going to choose x equals to just a, let's choose x equals to a to the power 3. Let's try that, okay? And the left-hand side, let's see if it works. It doesn't work, we're gonna keep looking, okay? So this is a to the power 3. And what would that be? The top is gonna be 3 times ln a over ln a. So ln a and ln n reduce, that's a 3. And the right-hand side is ln, this is a to the power 3, right? So what we get is we get ln, we first do the division inside, right? So we get ln a squared, and that's equal to 2 times ln a. So are these two the same? It depends on the value of a, right? But the left-hand side is always going to be 3. It's always going to be 3. Okay. And another situation, if you want to see better, okay, if you really want to see better, I really want to see they're not the same. Yes, if that's the case, I will give you another example. Okay. This other example, I'm going to choose a equals to e. Okay, I'm going to choose a equals to e, and x equals to e to the power 3. Okay, so in that case, let's see what's on the left-hand side. Right, so this is the left, and this is the right. Remember, we just need a one counter example to demonstrate it is not true. Okay, so we have a equals to e, so this is e. Okay, x is e to the power 3. Okay, so the left-hand side is going to be equals to ln e to the power 3 is 3, and ln e is 1, so the left-hand side equals to 3. And the right-hand side, x is e to the power 3, and a is e, sorry, this is e, and a is e. Okay, so that we're gonna get e to ln e to the power 2, that's going to be equals to 2. So this demonstrates to you solidly that 2 doesn't equals to 3. 2 doesn't equal to 3. Okay, so now let's look at number 19. Number 19, 3 times sine 2x equals to 2 times sine x. I mentioned this mistake during the lectures. Okay, this is a terrible mistake, but it's somewhat pretty common. It's somewhat very common. Okay, so don't make this mistake. So what is true about double angle of sine? What is true about it? The truth about sine 2x is equal to 2 times sine x multiply cosine x. Okay, so number 20. Number 20 says arctan of -1 is equals to 3 pi over 4. And the student would typically have an answer to it. Well, this is Wrong. Why it is wrong? Because arctan of anything, okay, the range is between negative pi over 2 to pi over 2. Okay. All right. Remember when we were talking about arctan, we have the no-fly zone. So arctan negative 1 is going to be equals to negative pi over 4. And the answer has to be here. And besides, you know, this is the, you know, the no-fly zone, etc., etc. Okay. Let me just show you that picture. The no-fly zone. Tangent, right? ARD. And let me make just some adjustment for what we have done before. Whether you use unit circle or not, it just use rectangular system, right? And it's a no-fly zone right here, okay? So cross. Okay, another one. All right, so the output, and of course there's this vertical line. This vertical line is not included either. So that's the no flight line. No flight line. Okay, so that's a forbidden line. Okay, so the domain and range, the domain of arctan. Okay, the domain of arctan. So arctangent. I mean, this function is used a lot in calculus. Quite a bit. Okay. The input is any real number. And the range is between negative pi over 2 to pi over 2. Right here. Okay. And this input is any real number, as we see in the arctangent picture. Okay, if you look at the arctangent picture, right? So let me show you the arctangent picture. What does it tell us? Right? Arctan picture. Give me a picture. These pictures are at our fingertips. And when we see that picture, we better know what it means. Right? When we see that picture, we better know what it means. Okay. Okay, I'm putting it right next to it. Okay. There's a horizontal span, vertical span, and there's you know, horizontal asymptote. There's horizontal asymptote. There are two of them. Right, the vertical span, the horizontal span. The domain is such. The domain is such because we can tell from the picture, right? The curve goes in both directions indefinitely. That's a horizontal span. Tell us the domain is from negative infinity to positive infinity right here. Okay, and the range is the vertical span. The vertical span doesn't go beyond the negative pi over 2, it doesn't go beyond the pi over 2 and cannot be negative pi over 2 or pi over 2 either. So that's open interval. Tell us the output angle from arctangent is not going to be beyond the negative pi over 2 to pi over 2. So that's the domain, that's the range, and the picture tells us so. The picture tells us so. Okay, so don't make that kind of mistake. So that's number 20. That's number 20. 21. 21. 21 is even, it's also a terrible mistake. Okay, I couldn't, I'm almost going to scream at this mistake. Okay. Arcsine and cosine. Okay, so I'm going to explain to you. This is a terrible, I would say horrible, horrible mistake. Okay, so let me explain how horrible it is. We just talked about arctan, right? We have arctan. We have all these information about arctan. Right, I want to bring it back. Right, that's about arctan. We know it. It's and on the left hand side, it's going to produce an angle. On the right hand side, right, the domain for sine for arc sine is between -1 to +1. The domain for arc cosine is between -1 to +1. And this domain is from -infinity to +infinity. You cannot even plug in. You cannot even plug in. Okay? Because if you plug in, say, x equals to 2, the left-hand side is defined, but the right-hand side is undefined divided by undefined. Okay? So you look at the domain, right? Domain on the left-hand side. And besides, even if you pick number between -1 to +1, and what are you going to what are you going to do about it? You have one angle divided by another angle. So if you look at the functions from domain and range perspective, right? So let's use this opportunity to review, this arc sine, right? Arc cosine. Arc sine, we take number between -1 to +1, and we take those ratio, right? We take those number as a ratio, and we serve as input for arc sine, and produces an angle. And the angle we produce, it's in the between -pi over 2 to pi over 2. Okay, and arc cosine, it also produces these, the domain are the same, and this is just arc cosine, but the angles are going to be produced between 0 to pi. Okay, if you look at all of these information, how are they supposed to work together? Right, they're not from the same domain. The domain are not the same on both sides. So this is a terrible, horrible mistake. Okay, it's shocking that we see this kind of mistake. It's even more shocking that we see these mistakes in calculus class. Okay, so don't make these mistakes. Okay, just take a closer look. And these are terrible, horrible mistakes. It's a shocking that, and sometimes I don't know, I cannot have more comments, and I don't want to be, I don't know what else to say. So don't make these mistakes. So 22, 23, we have these mistakes pointed out when we were talking about logarithm. So here, I'm going to talk about them again. Okay. So log base B. When we were talking about these topics, we certainly have gone through lenses to talk about it, but here I'm going to talk about this one more time. Okay, so this is wrong, right? This is wrong because we know the ladder, right? The ladder is equals to log base B, A times B. Okay, and this is true. This is true, but that is false. Okay, but do we have a counterexample for them? Easy, right? We have talked about counterexamples, right? Counterexample for there's so many counterexamples you could have. Okay, counterexample. For example, I can work with a base 2, right? I can work with a base 2, right? So if I can make a counterexample for base 2, that will be good, right? Or E, whatever. And then say I'm going to choose A equals to 2, B equals to 4, right? And the left-hand side is equals to 2 plus 4, right? So that's going to be equals to log base 2 of 6. And the right-hand side, I will have log base 2 of 2 and log base 2 of 4. So that's going to give me 1 plus 2 equals to 3. And that equals to log base 2 of 8. Are these two equal? Of course not. Of course not, right? So these terrible mistakes, please don't make them. Okay. Number 23 is that if we have subtraction, of course not, right? If we have subtraction, it's a terrible mistake. It's a horrible mistake. It's a very bad mistake. Okay, that's false. This is false. Okay, and the latter, what is true is the latter. The latter is equals to log base B of capital A divided by capital B. Okay, so that was a serious confusion right there. Okay. As far as the counterexample goes, and I can have a counterexample for this piece. Okay, so I'm going to create some counterexamples for you. Counterexample for this piece, right? And suppose I'm going to work with E. Okay, so if I have counterexample that work with E, then it works, right? So I have ln. Suppose domain and range is not going to be an issue. Okay, so ln. Will this be true? Because typically you'll see this kind of expression, this kind of mistake in calculus class. Most likely you're using ln. Okay, so I'm going to choose A equals to E squared. Okay, B equals to E. Okay, my left-hand side is ln E squared. My mouse is so tired, I think. e squared minus e. Okay, my right-hand side is equals to ln e squared minus ln e. Okay, and it's 2 minus 1 is equals to 1. Does that equals to 1? Because if this equals to 1, it should equals ln e, right? Are they equal? Well, not, let me put it here this way. Okay, 1 is equals to ln e. So if these two are the same, but e squared minus e is not going to be e. E squared minus e equals what? Get a numerical value. And e, this is 4 point something, right? E is 2 point something. So they're not the same, right? So this is another counterexample that's to say 23 is wrong. And of course, my examples require you to be more oriented with E, but please, you need to be, you need to know E very well. You're going to be dealing with natural logarithm in calculus all the time. You're not going to be seeing very much of a log base 2, log base 3. You're always going to be seeing ln, natural log. So you better be very good with E. Okay. So this is about 23. It's a terrible mistake, and we see it often. Okay, 24. Log base b of a over b is equals to these very common mistake. This is a terribly common mistake. Okay, exceedingly common, because I'm making the fonts larger. Actually, we already saw another form of this mistake. Okay, we did it a little bit earlier. I'm gonna bring it to us. It's later. It's ln, and there's one with a. Yeah, this one. Okay, recall this. These two are comparable. Okay, these two are comparable. The only difference is that these are natural log. So this is a, we know that this is a false. Right? We know this is a false. And that makes an example for this false. Okay, so this is a false. So what happened here is that the former is a quotient. You apply quotient rule. That's log base b, capital A, minus log base b, capital B. Okay, and this one doesn't equals to that. So they're different. And this one is, I don't know where, what else it can be connected to. It's just a terrible mistake. This is just a terrible mistake. Okay. So in order to leave you with any impression about this, I'm going to give you a counterexample. I'm going to give you a counterexample. Okay. For this counterexample, and because we're going to use natural log a lot, so I'm going to use for ln to show you how they are different, right? We already saw in example number 18, right? So here I'm going to show you another one. So here I'm going to have a equals to e to the power of 4 and b equals to e. Okay, and so the left-hand side is equals to ln, this is e to the power 4 divided by e, and that equals to ln e to the power 3. So that equals to 3. The right-hand side is equals to, okay, this piece, e to the power 4 over e to the power 3. I'm sorry, e, okay? And the top is 4, the bottom is 1. And that equals to 4. The 3 doesn't equals to 4, okay? I don't know how to prevent it. I don't know how to prevent it. What suggestion I can give you to prevent it? I think that you have to think about it when you do this. Okay, be aware that you might be making some mistakes. So at least you will double check. Okay, you will double check. For the people who make such a mistake, I keep thinking, they might be thinking, oh, I'm going to distribute this to A, distribute this to B. Could that be something they're thinking? No, it doesn't work that way. Because this piece, okay, let's look at another one. Okay, I'm going to give you another perspective. So hopefully that will prevent you from making this mistake, right? So I'm going to see, so similar to this, okay? So I'm going to give you another perspective. Hopefully you will never ever make this mistake. Okay, so I'm going to give you perspective from the order of operation. So the left-hand side, this mistake. Okay, this piece, meaning that you're gonna do A over B is the input for the function. Okay, and this function is a log base, and say this is it takes input. It produces an output. Okay, produces output. On the right-hand side, the perspective for the right-hand side, it basically says, okay, A is the input for this function, produces an output. Okay, let me put it this way. Yeah, let me do it this way. Okay, so A is given to the input, it produces an output. Okay, output, say output. And for B, it produces another output. Okay. Say this is output 2 and this is output 1. And then after these two outputs are produced, and we're going to take output 1 divided by output 2. And get a quotient. But here, you're going to do the quotient first and then give it to the function and produce an output. You can see the order of operation is completely different. All right. Okay, so now let's look at 25. Is another version of the same mistake. Okay, it just make base 10. So the same mistake could show up in different shape and forms, right? So this is the same mistake as 24 with the base 10. So of course this is a false. This is a false, right? And we can easily make we have counter examples. And for this case, you can easily make counter examples, okay, besides the order, right? So the order of operation perspective, right? So the order of operation perspective. So now it just, you just have this base 10, right? So this is base 10 and the order of operation are similar. So this is another version of number 24. And if you look at a counter example perspective, counter example, right? Counter example perspective, I can give you a counter example easily, easy. Okay, so this is a mistake, counter example to this piece. Okay, so we know this is a terrible mistake. So the counter example I'd like to give you, I can give you A equals to 100. Okay, B equals to 10. Okay, what would this be? And that would be left-hand side equals to, and this is 100, and this is 10. And that equals, we do the division first, right? So we get log 10 equals 1. And the right-hand side equals to that piece, right? This is 100, and this is 10. And we're gonna follow the order of operation, right? We follow the order of operation. So let me get you to see the order of operation here at the same time, right? So the top is 2, the bottom is 1. So that equals to 2. They cannot be equal. They cannot be equal. So that is all for these 25 questions. 25 questions that we've gone through that. We've done many of them throughout the semester in various capacities. So now it comes to final, and now I have led you guys to the gate of calculus class. So it's essential that you have clear understanding about these mistakes, and needless to say, many of these questions may show up on your final exam. So please make sure you do study them. And the answers to these questions has been permeated throughout the semester. Okay, as a matter of fact, when I started teaching, I started with the first question at the very beginning of the semester. Okay, also a lot of the mistakes and the right and wrongs that has all been addressed, Okay, so without further ado, I hope this lesson will be very helpful for you, not only for this course, it's also for the future, for your future course and your future success. Okay, if you have any further questions, please do not hesitate to reach out to me and I'll be happy to answer your questions. Okay, thank you for watching.